4.3 continued. We're talking about monotonic functions and the first derivative test. So the big deal here is the first derivative test, and we've already started this, and we really just need to do some additional examples to kind of solidify it. So we're jumping in here playing around with all these lovely polynomials and looking where they are increasing and decreasing based on their first derivative, the sign of their first derivative. Getting ready to move heavily into sign graphs in 4.3 and in 4.4. So again, hopefully you recall that quickly. So we will claim this, section 4.3 continued, and I'm just going to call it the first derivative test. When we go into the next section, we will also have a second derivative test. So this is just the first derivative test, and I should have capped all these things. This should be a capital, the first derivative test. Now we've already done one example, and so now we just need to go ahead and continue with additional examples. And so we're going to, I guess, start this with number 1 again. And they're going to give me a function, something like f of x equaling x to the 4th minus 8x squared plus 16. And they're going to ask me a whole lot of questions about this little function. They're going to ask me things like, what are the critical values? Where is the function increasing and decreasing? What are the extreme values? And extreme values, remember, are the maxes and the mins. And that's all they're going to ask right now. Then we move into the next section, they'll have more to ask us. So that's kind of a start as to what we're supposed to be doing with this function. So if we're looking for critical values, that's where you set the first derivative of the function equal to 0 or the first derivative function to being undefined, because that's going to give you your horizontal tangent lines, which should kind of define your local and max mins. And where it's undefined, that's where you have a vertical tangent line to the graph. So, so we're kind of playing covering all bases here. So if we take the first derivative of this function, this is nice and easy. It's going to be 4x cubed minus 16x. That's the first derivative. To find the critical values, and I'm just going to call it a CV, to find the critical values, there's 2 ways of doing this. One way is to set the first derivative equal to the 0, and the other is to find out what makes the first derivative undefined, and that's a UND for undefined. Well, for something to be undefined, really that means if you have a radical, like a square root, you don't need anything negative underneath it. Or if you have a rational, a fraction, that means don't let the denominator equal 0. Well, we don't have a radical or a rational, so we have no issues. So there is no place where this is undefined. So now we got to see if there's any place where it equals 0. So any place where 4x cubed minus 16x equals 0. Well, most definitely x being 0 is going to be one of them. Let's factor out a 4x, leaving behind an x squared minus 4. Still factoring, we get 4x times an x plus 2 times an x minus 2 equaling 0, and we are at this point completely factored. Then at this point, this is where you do the zero product property, where you set each one of these factors equal to 0, and you're going to get a value of 0 for x, a value of negative 2, and a value of 2. These are your critical values of your first derivative. This is where you're thinking some of these extreme values are going to happen. So to determine if these are local maxes or local mins, we go to a sign chart, where again a sign chart is SIGN chart. The sign, meaning is it positive or is it negative? You're looking for plus signs and minus signs. So when I go to a sign chart, I need to get these 3 critical values on my sign chart. These 3 critical values are a negative 2, a 0, and a 2. Put those on a number line, and then give yourself some, this is just really common, to put these dashed regions on the sign graph like that. We just always do that. That's just kind of standard method. Okay, so then what we do is we take a look at these 3 pieces of this product here, this factored version. One of them is a 4x, the other is an x plus 2, and the third is an x minus 2. We want to know the signs of these 3 factors, meaning is it positive or is it negative in this region? Well, to the left of negative 2, you can pick a test point. I don't know, negative 10. Any number to the left of negative 2. You could pick negative 100. Okay, just a number to the left of negative 2. If I choose negative 10, 4x would be 4 times negative 10, which is a negative 40, which is a negative sign. If I put a negative 10 into the x plus 2, it's negative 10 plus 2, which is a negative 8, which is a negative value. If I put a negative 10 into the x minus 2, it's negative 10 minus 2, which is a negative 12, which is a negative value. Well, your first derivative is the product of the 4x, the x plus 2, and the x minus 2. So that's a product of these signs. So it would be negative times negative times negative. Negative times negative times negative is a negative result. So the first derivative is negative to the left of negative 2. Now you look at the other region. And here between a negative 2 and a 0, well, probably negative 1. Okay, so check each one of these factors. 4 times negative 1 is negative 4, which makes it negative. Negative 1 plus 2 is positive 1, so that's positive. And negative 1 minus 2 is a negative 3, which is negative. So if the first derivative is a product of these three factors, then it's a negative times a positive times a negative, which is a positive result for the first derivative. So the first derivative is positive between negative 2 and 0. Now between 0 and 2, you can pick a test number of, say, 1. 4 times 1 is a positive 4, which is a positive outcome. 1 plus 2 is 3, which is a positive outcome. And 1 minus 2 is a negative 1, which is a negative outcome. So your product of the three would be positive times negative, which is a negative result. Last region would be to the right of 2, maybe a positive 10, maybe 100, whatever you like. If I choose 10, 4 times 10 is a positive 40, which is a positive outcome. X plus 2 would be 10 plus 2, which would be a positive 12, which is a positive outcome. And 10 minus 2 would be positive 8, which is, again, a positive outcome. So to get the product of these three, it would be positive times positive times positive, which is a positive result. So according to this first derivative test, the first derivative is negative to the left of negative 2, positive between negative 2 and 0, negative between 0 and 2, and positive between 2 and positive infinity. Now, this is the sign of the first derivative. According to this sign, my f of x function, which was x to the fourth, minus 8x squared plus 16, this original function, if the first derivative is negative, the original function must be decreasing in this region. If the first derivative is positive, my function, my original function, must be increasing in this region. Again, if the first derivative is negative, my function is decreasing in this region. And if my first derivative is positive, my original function, the x to the fourth function, is therefore increasing again. So your intervals of decreasing and increasing are listed right here. Now what's interesting is what's going on at these critical values. We've got 3 of these critical values here. Now let's think about this. If your function is decreasing, it's going down, and then it switches to increasing, coming up. So if it's going down and coming up, would this be a local max or a local min at negative 2? A local min. The next one, between a negative 2 and 0, your function is going up or increasing, and then between 0 and 2, it's decreasing. So if it's increasing and then decreasing, is 0 a local max or a local min? A local max. It's going up and then coming down. So it's going to go up to a peak or a maximum. Then at 2, your function was decreasing and then increasing. So if it's going down and then up, is this a local max or min? A local min. Okay, so what we've concluded so far is this function has 3 extreme values. Now, I'm not for certain whether any of these are absolute. Now, if I wanted to know if they were absolute or not, I'd come up here and think again, what is this function? This is a 4th degree function, right? So if it's a x to the 4th, meaning a 4th degree polynomial. If it's a 4th degree polynomial, the end behavior is up and up, okay? Up on the left and up on the right, and somewhere in the middle, I don't know what it's doing. But on the ends, it's both going up, so there's no way we have an absolute max, but it's a good chance we have an absolute min. So, one of these is probably an absolute min. I don't know which of these, but one of these is probably an absolute min. So really, we could go in and plug in these values, find the function values for these. So in order to find the absolute extrema, meaning we're looking for an absolute min, because we already know there's not going to be an absolute max on this 4th degree function. So I go to my function, my original graph of my original function, and I say, well, what is f at negative 2? And what is f at positive 2? Now, if you plug these in to the original function, this is f of x. This is going back to f of x equaling x to the 4th minus 8x squared plus 16. If you plug a negative 2 in, this is going to equal 0. If you plug a positive 2 in, it's going to equal 0. Okay? And if you want to, you can go ahead and evaluate your local max. And if you put a 0 in, you're going to get 16. So there's some values for you. So it appears that you got to have an absolute min at 0, and both of them really are absolute, and a local max at 16. Now, once you've written that, you may not feel confident that you have the right answer. So here's where it would be very wise to pick up your calculator and see if all this information is right. Okay, see if you've done this correctly. And because you do have that powerful calculator, there's no reason why not to use it to confirm our work. So here's my graph now. I'm going to go to the calculator and check what's going on. Okay, so I'm going to have y, my original function, equaling x to the 4th minus 8x squared plus 16. What I think is happening, before I graph it actually, let's write what we think is happening. We think that our function, according to this sign chart, is decreasing from negative infinity to negative 2, and also from 0 to 2, right? That's what we say in our chart up here. That red line. How do I make it go away? You'll always tell me how to do this. Okay. Okay. So then we're going to do increasing. My function is increasing according to my sign graph here. It's increasing between negative 2 and 0. These are intervals, not ordered pairs, but intervals. And then also increasing between 2 and positive infinity. We believe that there is a local max of 16 occurring at x equaling 0. And we believe that there really are two absolute mins of 0 occurring at the x values of negative 2 and 2. Okay, that's what we think is going on. Okay, we feel pretty good about this, but before we want to submit this as our complete, certain 100% got it right, that's where we go to the calculator and graph this, and then we confirm if we're on track or not. So let me go to my calculator. Here it is, and put in here y is x to the power of 4, 4th degree polynomial, minus 8x squared plus 16. And these numbers are all around negative 2 and positive 2, because I really don't need a very big window. I might just do a zoom standard, because I don't need a big window, because we're looking at these critical values of negative 2, 0, and 2. So there's nothing large happening here on my x's. So let's just do a simple zoom standard window, and there it is. There's a W-shaped graph. The end behaviors are up here on the left. It's going up and up on the right. Here's my negative 2 and my positive 2, so those are definitely absolute mins. We're good. This up here is bound to be a local max, but I can, if you want to play around with the window, if we want more y values, we can let y max be instead of 10. Maybe you want, I don't know, 100 might be overwhelming, but we can try it. There you go. Now you see the W. Okay, the standard 4th degree polynomial graph kind of thing. So there it is. So I feel pretty darn confident that I have absolute max going on at 0 and a local, absolute mins at a height of 0 and a local max at a height of whatever we said it was, 16. So this looks good. So now I can kind of look at it and get this window off and go back to the screen. So it looks like this, and it follows all of our data. 0, negative 2, and 2. It was coming down, and then way up here high at 16. So it was coming down, going back up, coming back down, and going back up. So we got the locals, maxes, and mins good. Now, are we decreasing, increasing correctly? Are we decreasing from negative infinity to negative 2? Is the function going down here from left to right? Yeah. Are we decreasing from 0 to 2? Yes. Are we increasing from -2 to 0? Yes. And are we increasing from 2 to infinity? Yes. So we have nailed it. We have done well. We have it all right. Okay, so that's kind of the process we're going through. Now let's look at another example. Again, we need to be good at this. Not just kind of good. We need to be good at this. So let's do another example. And it is so nice to have that calculator to kind of verify our work and to further solidify that we know what we're doing. Okay, so really it's the same kind of question. I want to know critical values. I want to know extrema. I want to know where it's increasing and decreasing. Okay, these standard questions. Just make it all happen. Answer all of it. And here's what the function looks like. This one is an x squared minus 3 over an x minus 2. Well, you can tell right now we got a new level of difficulty. We have a new level of difficulty. This is a rational function. It definitely has a vertical asymptote at 2. It's going to be doing some wild stuff. So we need to take a look at this one. So this is going to be kind of different. All right, so let's go ahead and play with this. Let's come in here and let's come up with the first derivative of this function. Well, the first derivative of this function is the bottom times the derivative of the top minus the top times the derivative of the bottom, all divided by the bottom squared. Bottom times the derivative of the top minus top times the derivative of the bottom divided by the bottom squared. So this becomes 2x squared minus 4x minus x squared plus 3 over this x minus 2 perfectly squared. Which equals a negative x squared minus 2x, not 2x. X squared, gotcha. X squared minus 4x, right, plus 3 all over x minus 2 squared. That's a 4x. Okay, so now I'm going to come back over here. So this is what? This is x minus 3 times x minus 1 over x minus 2 perfectly squared. All right, that's my first derivative. Okay, to find my critical values of my first derivative, there's two ways of doing it. Set the first derivative equal to 0 and determine where the first derivative is undefined. Okay, when I set it equal to 0, I really only set the numerator equal to 0, which is going to give me the values of 3 and 1. When I set it to be undefined, that's when the denominator needs to equal 0, which would make a fraction undefined. And this is where the x value is 2. So we have 3 critical values. So I take my critical values and I put them on a sign chart. So I have a 1, 2, and 3. That's interesting. A 1, a 2, and a 3. This might not be fun. Okay. Okay, and remember your first derivative, I guess I should put it right here. Your first derivative is x minus 3 times x minus 1 over x minus 2 squared. So you're going to have a factor of x minus 3, a factor of x minus 1, and a factor of x minus 2 times x minus 2. I guess that's the best way of writing it. Okay, pick a checkpoint over here, a test point 0. 0 minus 3 is a negative 3, which is negative. 0 minus 1 is a negative 1, which is negative. 0 minus 2 is a negative 2, which is negative. And 0 minus 2 is a negative 2, which is negative. Now, you got a negative times a negative on the top and a negative times a negative on the bottom. So would this rational, according to these negative, negative, negative signs, is this going to be positive or negative? It's going to be positive because it's a negative times a negative over a negative times a negative, which is a positive over a positive. Okay, now pick a number in here, which would be like 1.5. 1.5 minus 3 is a negative 1.5, which is negative. 1.5 minus 1 is a positive 0.5, which is positive. 1.5 minus 2 is a negative, and 1.5 minus 2 is a negative. So now you have a negative times a positive on the top, and a negative times a negative on the bottom. A negative result. Okay, between 2 and 3, suppose you pick a test point of 2.5. 2.5 minus 3 is a negative 0.5. 2.5 minus 1 is a positive 1.5. 2.5 minus 2 is a positive 0.5. And 2.5 minus 2 is a positive 0.5. So you have a negative times a positive over a positive times a positive, which is a negative result. He wants to do 4. I want to do 10. I like 10. Pick a point over here, 10. 10 minus 3 is a positive 7, which is positive. 10 minus 1 is a positive 9, which is positive. 10 minus 2 is a positive 8, which is positive. Positive. So this is definitely positive. Okay. So that's your signs on your first derivative. Your first derivative is positive, negative, negative, positive. So your original function, this x squared minus 3 over x minus 2, your original function must therefore be increasing, then decreasing, and then increasing according to the signs of the first derivative. So if it's increasing, it's going up and then coming back down. So it's going up and then coming back down. Would this indicate a local max or a local min? Local max. If it's going down and then it's going down again, is there anything happening here? Probably. Is that my undefined place? Yeah. Okay. Okay, so this is like we're not certain what's going on here. Okay, probably an asymptote. And then if I'm decreasing and increasing, is this a local max or a local min? Local min. Okay, so we conclude, and we'll check our conclusion by picking up the calculator. Our conclusion is our function is decreasing from 1 to 2 and from 2 to 3. And I'm going to eliminate the number 2 because there's probably a vertical asymptote. Something's there. We already said a vertical asymptote was there, okay? So we're going to leave 2 out of the picture. Then we have this original function is increasing from negative infinity to 0 and from 3 to positive infinity. And I should put a u in here. That means the union of those two intervals. Yes. What am I thinking? Oh, I'm seeing my test point. Probably be better if I use colors or something on here so I can see my critical values. Remember, my critical values are 1, 2, and 3. Okay? I project that I have at least a local max, which is going to be what? At f of 1? A local max when x is 1? F of 1 is what? 1 squared minus 3 over 1 minus 2, which is what? A negative 2 over a negative 1, which is a height of 2. And I project that I'm going to have a local min at f of 3, which is 3 squared minus 3 over 3 minus 2, which is 9 minus 3, which is a 6. So I project I have a local max at 2 and a local min at 6. And I'm not so certain about the absolute stuff because the end behavior on this thing, the end behavior is probably down on the left and up on the right. Okay. Okay, so I kind of think that there's not going to be any absolutes happening here. So now all we have to do, and maybe we should actually put this on here, our critical values were where x was 1, x was 2, and x was 3. And I think we've answered pretty much everything they're going to ask me. So your local max is 2, occurring at x equaling 1. Your local min is... What have we done wrong here? That doesn't make any sense at all. Well, let's look at the graph. Let's look at the graph. Okay, what do we have here? We have x squared minus 3 over x minus 2. So, oh, wrong calculator. I picked up my manual one. I'm holding a calculator in my hand. Like, that does a lot of good, you guys. Okay. Okay. It is not easy to do all this at the same time. I am seriously multitasking up here. Okay, x squared minus 3 divided by x minus 2. Okay, and we're looking like from 0 to 3. We don't have very big numbers. 2. I'm just going to keep it at a zoom decimal. Or return it to a zoom decimal, whatever. Hit there. That is strange. That didn't work. Okay, I didn't get the whole picture. So I'm going to go to the window, and I'm going to give myself a larger Y max. Well, I might want to do it my way. There we go. It's kind of funny looking. Okay, let's see if we can duplicate this lovely graph. So it's very obvious that there's a vertical asymptote right here, right? Okay, so when we graph it, and I'll come to my piece of paper here in just a second. Okay, it looks like something like this. Right. There we go. Looks something like that. So when we got that a local max of 2 when x is 1, when x is 1, a height of 2 right here. Yep, that's right. And then we got a local min at 6 when x is 3 right here. Then, yeah, I guess that's right. And there are no absolutes because this is heading out this way, and this is going this way. And I didn't put my oblique asymptote in here worth a darn, but I'm certain there is an oblique asymptote that should be moving right through all of that. So, and because of my window, it doesn't draw a line right here on this vertical asymptote on the calculator. I can't show it. Okay. So if you did a zoom standard, didn't you get a line there? Did you get a solid line there or not? Yeah, okay. You know why it does that? Because it's connecting a point way down here to a point way up here. It's in connected mode. So it connects. We did good then. It's kind of a weird answer, but it worked. Lots of work. Okay. Takes more and more practice before you get good and competent. But you'll get there. Let's do a trig one. That should be fun. These are kind of time consuming, but it is neat when you get it right. Don't y'all agree? It's like, ooh, I'm good. Okay, let's talk about critical values. Again, we're talking about extrema. We're talking about increasing and decreasing stuff. I guess that's it. And here's the function. F of x equals the square root of 3 times cosine x plus sine x. Now, what in the world does that look like? I have no clue. I would have to graph it. But we're only looking from 0 to 2 pi. And they're limiting us. We don't have to go out forever in this rolling, these periodic graphs. All right, so figure all this out, all this increasing, decreasing, and extrema stuff. We need the first derivative. So here we go. The first derivative, the derivative of cosine is a negative sine x. This is a negative square root of 3. Sine x times the derivative of x, which is 1, so that's it. And the derivative of sine is cosine. Now, to find the critical values, there's two ways of finding this. One is to set f prime of x equal to 0, and the other is to determine where f prime of x is undefined. Well, with these trig functions, we don't have any undefined situations. Now, if you had tangent, you would, okay? Or you started getting the co-functions like cosecant and cosine, cosecant and secant, then those aren't the co-functions, those are the reciprocal functions. Then you'd start kind of playing around with some undefined situations. So we got to figure out how to set this thing equal to 0. Y'all remember how to do this? Let's move this sine x to the other side. This would be cosine x equaling a positive square root of 3 of sine x, right? Then if I divide both sides by cosine x, I'd have 1 equaling the square root of 3 of sine x over cosine x, or I would have 1 equaling the square root of 3 tangent x. Or I would have 1 over the square root of 3 equaling tangent x. Those numbers should look kind of familiar. Square root of 3 stuff. Oh, yeah, trig. Trig mess. Trig stuff. So what in the world must x, or what in the world are the values of x? What are the angle values of x such that tangent of x is 1 over the square root of 3, which is the square root of 3 over 3? Well, I have always done this with right triangles. You guys might know it by heart. But if this is a 30-60 triangle, this is 1, 2, and the square root of 3. So for tangent to be 1 over square root of 3, that's got to be 30 degrees, or pi 6, right? So x is pi 6. Well, for tangent to be positive, it's only positive in quadrants 1 and quadrants 3. So it's pi 6 in quadrant 1, but in quadrant 3, this would be 7 pi 6. Okay, so there are the solutions that would cause the first derivative to equal 0, which I'm going to use in my sign chart. It's kind of fun. Y'all remember that? Kind of, a little bit? It's been a while. If you're used to the unit circle instead of the right triangles, then you might want to refresh yourself on the unit circle values. Okay, so here comes the sign chart. It needs to have pi 6 in it, and it needs to have 7 pi 6ths in it. The sign chart might look a little weird because f prime of x this one might be a little harder to come up with. F prime of x is a negative square root of 3 sine x plus cosine. It's not a product, so all this sign chart business might not work so beautifully, right? There's actually some math here. So if we did a negative square root of 3 sine x, and we did a cosine x, we're adding these things together, right? We're adding them. Okay, let's pick 0. Sine of 0 is 0, so this would be 0, and cosine of 0 is 1, so 0 plus 1 would make this a positive 1. So this would be positive. If I'm between pi 6 and 7 pi 6, that's going to include pi. So sine of pi is 0, and cosine of pi is negative 1. So 0 plus a negative 1 is a negative 1, which makes this a negative sign. If I pick 2 pi Sine of 2 pi is 0, so this would be 0, and cosine of 2 pi is 1, and 0 plus 1 is a positive 1, which is a positive result. So the sign chart isn't quite the same here because we don't have a product. So this sign chart is kind of weird. Okay, it's not a normal sign chart, but it gives us the signs. We figured out the signs, okay? That's all we need to know. So therefore, that's the first derivative. So the original function, who is the square root of 3 cosine x plus sine x, must therefore be increasing, then decreasing, and then increasing again, according to the signs of the first derivative. So if it's changing from increasing to decreasing, up and then down, this is probably a local max. It might be an absolute max, right? This is a rolling function. So then here at 7 pi 6, if you're decreasing and then increasing, you're going down and then you're going up. Is this a local max or local min? Local min. And these are going to be absolute, no doubt. Okay, now remember, now this is interesting because in order to determine your absolutes, when you have a select interval to work in, you have to check the endpoints, remember? So you have to check the endpoints. Anytime they limit your picture, anytime this is not just all real numbers or negative infinity to infinity, you've got to watch these endpoints on these extrema. So let's think about this. So at this point, we can conclude that with this limited range of 0 to 2 pi, we believe this original function is increasing from 0 to pi 6, and then also from 7 pi 6. Oh, that's hard to read, but that says 7 pi 6. My pen is like sliding all over the place. To 2 pi. We believe it is decreasing between pi 6 and 7 pi 6. We're not certain about these extrema, but we know something's going on at pi 6 and something's going on at 7 pi 6, and we know we better check out those endpoints. So let's find f of pi 6, f of 7 pi 6, and then we better check the endpoints of 0 and 2 pi before we determine who's absolute and who's local. So remember, f of x is the square root of 3 cosine x plus sine x. So at pi 6, oh, I didn't leave a whole lot of room here. This is the square root of 3 times the cosine of pi 6 plus sine of pi 6. Well, cosine of pi 6 is square root of 3 over 2. So that's 3 halves. So this is 3 halves. Sine of pi 6 is 1 half. So that's 4 halves, which is 2. 7 pi 6. This becomes a square root of 3 cosine of 7 pi 6 plus sine of 7 pi 6. Okay, cosine of 7 pi 6 is square root of 3 over 2, but in quadrant 3 it's a negative square, it's going to be a negative 3 halves, right? It is a negative 3 halves. And sine of 7 pi 6 is a half, but it's in quadrant 3, so it's also negative, so it's a negative 2. 0. Thank goodness something doesn't have to think so hard. Cosine of 0 and then sine of 0. Cosine of 0 is 1, so this is the square root of 3 times 1, and sine of 0 is 0, so this is just a square root of 3. And then this is going to be the same thing at 2 pi. Cosine of 2 pi is 1 times the square root of 3 is the square root of 3, and sine of 2 pi is 0, so it's square root of 3. Okay, so who's absolute? We evidently we thought there was a local max at pi 6, and it's not just local, but it's absolute, right? So we have an absolute max of 2 at x equaling pi 6, and we have an absolute min of negative 2 at x equaling 7 pi 6. So remember, your maxes and mins are your y values occurring at an x. Now, I wonder if we're accurate. This is when you pick up the handy-dandy little calculator and let her roll. Okay. This is trig stuff. So this is square root of 3. Cosine x plus sine x. I'm going to go to the mode button and make certain this thing's in radian mode. And it is. Then I'm going to do a zoom trig. Which is going to take me from negative 2 pi to 2 pi, so I really only want the right half. And what is the problem with this? I'm going to have to do a zoom standard first, I think. I think I've got this window so messed up. Let's clear it up. Well, if I standardize the screen, that tends to help. And then I'll go back and trig it. Isn't that pretty? Okay. Zoom. Down, down, down. 7, but then y'all can't see what I'm doing, except for to look over there at this mess. How would you like to try to figure out what all that says? Just enough to make anybody confused. Okay, so we're going from 0 to 2 pi. So we're only looking at the right half, from 0 to 2 pi. So we said a height of 2 was our absolute max. A low of negative 2 was an absolute min. We said that we were increasing from 0 to 6 pi. This is the 0 to pi 6. This is the 0 to pi 6 region. And then we were increasing from 7 pi 6 to 2 pi, which is this region. From here up, that's 7 pi 6 to 2 pi. We're going up. Then we say we're decreasing from pi 6 to 7 pi 6, which is from here to there. We did good. Right? We did good. So I'm going to duplicate it. You probably should go ahead and duplicate this in your notes too, so you're also seeing the graphical version of what's happening here. Okay, so my duplicate, my very quick duplicate of the graph looks something like that. This is your max at 2, which is occurring at pi 6. This is your min of negative 2 occurring at 7 pi 6, which gives you a vision of where it's increasing, decreasing, increasing, and your local max, or excuse me, your absolute max and your absolute min. There are no arrows on the ends of these lines because they limited my domain. So there's no arrows, and that's why we have well, we're going to have absolutes anyway. Okay. So there is a trig version. You'll be really careful. They should stay consistent even in your homework, where you're probably, if you have a sine and a cosine like that, whenever you try to solve it for equaling your first derivative equaling 0, you're going to play around with the tangent function. And somewhere in some examples, I've seen them do some of the sine 2x being 2 sine cosine theta. Here's an identity. You may or may not run into this into your homework, but you might want to write this down. If you have sine of 2x, it is 2 sine x cosine x. And I have seen this somewhere. I don't know when I did some of these examples, but you might run into that. So just remember, you might have to use that double angle identity when you're working on your homework. I'm not certain where I've seen it, but it's been recent. So just kind of keep that in the back of your mind. That, my friends, is the end of section 4.3. And I think we all could handle a break anyway, so that's very good timing.